Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about the module Permutation Symmetry in Quantum Mechanics from the paper Quantum Mechanics 1. The main points that we are going to be covering in this module are the principle of indistinguishability of identical particles, then how the problem of identical particles is treated differently in quantum mechanics from that in classical mechanics. Then we will also try and understand the properties of permutation operator and how to construct the completely symmetric and completely antisymmetric wave functions. We will also get to know the definition of fermions and bosons. Then we'll also know the connection between the spin and statistics and learn Pauli's exclusion principle. In this module, we shall also study the role of the permutation symmetries to describe a system of identical particles in quantum mechanics. Two particles are said to be identical if all their intrinsic properties such as mass, charge, spin, etc. are the same. For example, all the electrons or protons or alpha particles or hydrogen atoms in the universe are identical. On the other hand, an electron and a positron are not identical since although they have the same mass and same spin, but they do not have the same charge. We shall see that unlike in the case of classical mechanics, where the identity of particles in a system does not pose any particular problems, in quantum mechanics, however, to describe a physical state, the kets are required to be either completely symmetric or completely antisymmetric, depending on the nature of the identical particles. With respect to the permutation of these particles, we shall introduce permutation operators and discuss their basic properties. We shall extend the study from a system of two identical to many particle systems and describe to construct completely symmetric and completely antisymmetric states. Those particles for which the physical kets are symmetric are called bosons, and those for which they are antisymmetric are called fermions. Particles of half integral spins in units of h cross, that is h cross where h cross is equal to h by 2 pi and h is the Planck's constant, are fermions, which are known to obey Fermi-Dirac statistics, and those with zero or integral spins are called bosons, which obey the Bose-Einstein statistics. Principle of indistinguishability of identical particles. Two particles are said to be identical if all their intrinsic properties such as mass, charge, spin, etc. are the same. Examples: electrons, protons, hydrogen atoms, etc. In the case of system of identical particles in quantum mechanics, observation of an individual particle is not possible without affecting the dynamics of the system. For example, in proton-proton scattering, the proton which is received by the detector could be either the target proton or the projectile proton. It would not be possible to detect which one is which. This is the principle of indistinguishability of identical particles. Significance of symmetry in quantum mechanics versus classical mechanics. The identity between the target and the projectile protons in classical mechanics implies that if we have a target which is struck by a projectile and both the target and the projectile are protons, then in the scattering process that ensues, the scattering cross-section is the sum of those corresponding to the process that is shown in the figure, where you have 1, the first proton, which is being denoted by the wave vector k, after scattering has the wave vector k prime, while the second proton also gets scattered, and the angle which the wave vector 1 makes with the original direction after the scattering, that is the angle which the scattered proton 1 makes with the original direction, or the angle between the wave vector k prime and the wave vector k, is given by theta and phi. Now in figure 2 we can also write this as another way of explaining this, that the proton 2 and the proton 1 act either as target or projectile and get scattered. In this case, the proton 1 having initial wave vector k gets scattered with the wave vector k prime, while the proton 2 gets scattered in the other direction towards the detector. And here the angle of scattering is given by pi minus theta and pi plus phi for the two protons respectively. Now here it is important to see that the proton 1 going to the detector or the proton 2 going to the detector, so it's difficult to find out which of the two was the projectile and which of the two was the target. Now in case of classical mechanics, this scattering is basically, if you want to find out the total scattering cross section, then it is the sum of these two processes, that is the scattering cross section as determined by these two processes, wherein in one case the detector detects the projectile proton, while in the other case the detector detects the target proton, and the total scattering cross section is the sum of the scattering cross section of the projectile proton and the target proton. However, in quantum mechanics this is not the case, and here the superposition is of the amplitudes and not of the cross sections of the scattered protons. Principle of indistinguishability. Now, in the case of quantum mechanics, like mentioned earlier, the superposition is not of that of the cross sections as measured for the two protons, but the superposition is of the scattering amplitudes. These amplitudes are to be added or subtracted is decided by the spin of the particles. Now here this is something which is very important to understand. In classical mechanics, there is no concept of spin, whereas in quantum mechanics, the concept of spin is extremely important. And like we have just discussed, that whether the scattering amplitudes in this kind of a scattering process are to be added or subtracted is decided by what is the spin of the particles. And here, in case of quantum mechanics, the superposition of the two scattering amplitudes would give an interference term which has no analog in classical mechanics. Now, let us discuss in detail the principle of indistinguishability, which in case of classical mechanics does not exist. So, according to the principle of indistinguishability, the physical observable, that is, the Hamiltonian of the system that is being studied, should be invariant under the interchange of the two particles. So like when we were discussing in the earlier figure, you have two protons, one which is the target, the other which is the projectile. So in case of quantum mechanics, if you write down the Hamiltonian of the system, even if you interchange the two protons, that is, the proton which was earlier acting as the projectile is now made to act as the target, while the proton that was earlier acting as the target is now made to act as the projectile. Your total Hamiltonian of the system would remain unchanged even with the interchange of these two particles. That is, it would be invariant. Mathematically, we can express this as Hamiltonian operator H of the particle 1 and 2 is equal to Hamiltonian operator H of the particle 2 and 1, where the Hamiltonian operator H of the particle 1 and 2 stands for the Hamiltonian where particle 1 is in state alpha and particle 2 is in state beta, or if we look at the example that we just considered, proton 1 is the target and proton 2 is the projectile, and vice versa in case of Hamiltonian operator H acting on particle 2 and 1, where particle 2 is the target and particle 1 acts as the projectile. So in this manner, one can see that if one interchanges the target and the projectile, so long as both of them are protons, the total Hamiltonian of the system remains invariant. Similarly, we can also write for the wave function psi12, where psi12 is the wave function with particle 1 in state alpha and particle 2 in state beta, and psi21, where psi21 is the wave function with particle 2 in state alpha and particle 1 in state beta. Symmetrizing the wave functions. So now, considering the same case, that is, considering the principle of indistinguishability, we now use this principle on the wave functions. So if we consider two wave functions, psi12, where the wave function psi12 refers to particle 1 in state alpha and particle 2 in state beta, then the Schrodinger equation for this wave function can be written as iota times h cross times partial derivative with respect to time of the wave function psi12 is equal to Hamiltonian operator h12 acting on the wave function psi12. Now if we interchange the two particles, that is, now particle 2 is in state alpha and particle 1 is in state beta, then because of the invariance of the Hamiltonian, we can again write the Schrodinger equation as iota times h cross times partial derivative with respect to time of the wave function psi21 is equal to Hamiltonian operator h12 acting on the wave function psi21. From this, it follows that if the wave function psi12 is a possible state with certain energy, then so is the wave function psi21, and that both these wave functions have the same energy. This result in classical mechanics has no significance. However, in quantum mechanics, this result makes all the difference when we apply the superposition principle, according to which any linear combination of these is also a possible solution. That means if we have these two types of wave functions, psi12 and psi21, for which the Hamiltonian operator remains invariant, then we can write two linear combinations of these wave functions. One that is given by psi subscript s12 is equal to 1 upon under root 2 whole times bracket open wave function psi12 plus wave function psi21 bracket close, where alpha is not equal to beta. That means the state alpha is not equal to the state beta or equivalent to the state beta. And the other wave function that we get as a linear combination of these two wave functions is psi subscript a 1 2 is equal to 1 upon under root whole times bracket open wave function psi 1 2 minus wave function psi 2 1, again with the same condition that the state alpha is not equivalent to the state beta. Properties of permutation operator. Now, the way in which we have defined our linear combination of the two wave functions psi12, where wave function psi12 denotes particle 1 in state alpha and particle 2 in state beta, and psi21, where the wave function psi21 denotes particle 2 in state alpha and particle 1 in state beta, and the linear combination denoted by psi subscript s12 and psi subscript a12, then here we see that the wave function psi subscript s12 is symmetric, while the wave function psi subscript a12 is antisymmetric wave function under the permutation of particles 1 and particle 2. That is, if we interchange the two particles, then the symmetric wave function, that is psi subscript s21, turns out to be equal to the original wave function, that is psi subscript s12, while if we interchange the particles 1 and 2, then the antisymmetric wave function, that is psi subscript a to 1, turns out to be equal to the negative of the original wave function psi subscript a 1 2. This property of the two linear combinations, one being symmetric and the other being antisymmetric under the permutation of the two particles 1 and 2, leads us to introduce the permutation operator P12, which represents the exchange of particles 1 and 2. So, permutation operator P12 acting on wave function psi 1 2 yields the wave function psi 2 1. That means the effect of the permutation operator P12 acting on the wave function 1 2, where wave function 1 2 denotes particle 1 in state alpha and particle 2 in state beta, yields the wave function where particle 2 is in state alpha and particle 1 is in state beta. By operating twice, that means if we again operate the permutation operator on this previously discussed equation, one can see that we get back the original wave function. So in this manner, one can write that the square of the operator P12 turns out to be the identity operator, having eigenvalues +1 and -1 depending upon the type of the wave functions being used. That is, if the wave function is symmetric, that is psi subscript s 1 2, then the eigenvalue is +1, and if the wave function is antisymmetric, that is psi subscript a 1 2, then the eigenvalue is -1. Permutation operator, like the parity operator, is both Hermitian and unitary. That means that the permutation operator is equal to its inverse as well as equal to its adjoint, and thus it can be shown that the permutation operator commutes with the Hamiltonian, or writing it mathematically, permutation operator 1 2 acting on Hamiltonian operator 1 2 is equal to Hamiltonian operator 1 2 acting on the permutation operator 1 2, or the commutator of the permutation operator 1 2 and the Hamiltonian operator 1 2 is 0. Invariance of Hamiltonian under permutation. The invariance of the Hamiltonian under the transformation of permutation operation implies that the eigenvectors of the Hamiltonian operator are the eigenvectors of the permutation operator P12. Also, the permutation operator thus represents a conserved quantity. If the wave function of the system at one instant is even or odd under the interchange of particles, it will remain even or odd for all time. This can be seen directly from the Schrodinger's equation. These considerations can be extended to a system of n identical particles where we will have n into n minus 1 by 2 exchange operators given by exchange operator Pij, all of which now commute with the Hamiltonian of the system. So the commutator of the permutation operator or the exchange operator Pij with the Hamiltonian operator H is equal to 0 for all I going from 1 to n minus 1 and j going from 2, 3 to n. These exchange operators do not, however, commute among themselves. That is, the expectation operator, the exchange operator Pij and exchange operator Pjk is not equal to the exchange operator Pjk, exchange operator Pij. As a result, we shall not have a complete set of functions which are simultaneous eigenvectors of all the exchange operators and the Hamiltonian operator H. But since all the exchange operators commute with the Hamiltonian, therefore there should exist at least one wave function that is a simultaneous eigenvector of all the exchange operators and the Hamiltonian operator H. Symmetry of the wave function. Now suppose that phi is such a function so that one can write the eigenvalue equation as Hamiltonian operator H acting on phi is equal to the energy eigenvalue E times the wave function phi, and the permutation operator Pij acting on the wave function phi yields the eigenvalues lambda ij times the wave function phi, where I goes from 1 to n minus 1 while j goes from 2 to n, where lambda ij is equal to plus or minus 1. And for any three different values of ijk, the permutation operator Pij acting on the permutation operator Pik is equal to permutation operator Pjk acting on permutation operator Pij, and this is equal to permutation operator Pik acting on permutation operator Pjk. And using this equality, one can say that, and also the above equations involving the Hamiltonian and the eigenvalue form of the equation for the wave function phi, one sees that lambda ij times lambda ik is equal to lambda jk times lambda ij is equal to lambda ik times lambda jk, or lambda ij is equal to lambda ik is equal to lambda jk. What this means is that all the exchange operators acting on the common eigenvector has the same value, either plus 1 or minus 1. And these equations then lead us to a very important result, which can be stated as that the wave function of a system of identical particles is either totally symmetric or totally antisymmetric. Spin and statistics. Symmetry character of the wave function is, in fact, an intrinsic property of the particles. A system of particles such as electrons or protons is described by antisymmetric wave functions, while a system of photons or pions is described by symmetric wave functions. Particles of first category obey Fermi-Dirac statistics and are called fermions, while that of the second category obey Bose-Einstein statistics and are called bosons. Fermions have half-integral spin in units of h cross by 2, while particles with zero or integral spins are bosons. Pauli's exclusion principle. Now, we know that the fermions have half-integral spins, whereas the bosons have integral spins. So, if we want to write down the wave function of two spin half particles, that is two fermions, then we know that the wave function is antisymmetric. So, if the wave function phi alpha subscript alpha 1 and wave function phi subscript alpha 2 represent the two quantum states that are available to these two fermions having spin half, then the wave function of the system of these two fermions can be written as antisymmetric wave function psi subscript a 1 2 is equal to 1 upon under root 2 factorial whole times bracket open 1 minus permutation operator p 1 2 bracket close times wave function phi subscript alpha 1 1 wave function phi subscript alpha 2 2. Here one can see that this antisymmetric wave function, which denotes the complete state of the two particle system that we are considering, that is the two fermions with spin half, whose individual quantum states are represented by the wave function phi subscript alpha 1 and the wave function phi subscript alpha 2. This antisymmetric wave function vanishes. That means psi subscript A12 vanishes when phi subscript alpha 1 is equal to phi subscript alpha 2, or when the two quantum states are equivalent. And the reason for this is that this antisymmetric wave function psi subscript A12 can be represented as a Slater's determinant. That is, mathematically it can be written as 1 upon under root 2 factorial whole times determinant of phi subscript alpha 1 1, phi subscript alpha 1 2, in the second row phi subscript alpha 2 1, phi subscript alpha 2 2, where phi subscript alpha 1 1 represents the first fermion in state alpha 1, and phi subscript alpha 1 2 represents the second fermion in the state alpha 1. Similarly, phi subscript alpha 2 1 represents the first fermion in state alpha 2, and phi subscript alpha 2 2 represents the second fermion in state alpha 2. So, from the Slater's determinant, it is clear that it is impossible for the two fermions to occupy the same quantum state. And this is the essence of the Pauli's exclusion principle. The above equation, written for two spin half particles or two fermions, can be generalized to the n particle case and can be represented mathematically as psi subscript a particle 1, 2, so on, n is equal to 1 upon under root n factorial whole times summation over p minus 1 to the power pi p times permutation operator p acting on the states phi subscript alpha 1 1, phi subscript alpha 2 2, and so on, and phi subscript alpha n n, where p represents one of the n factorial permutations and pi p is the number of the two particle exchange operators contained in the permutation operator p. Wave function for bosons. Now, like we discussed earlier, that half integral spin particles are fermions, while particles which have no or integral spins are bosons. So let us now discuss that if we want to write down the wave function for a system of particles which are bosons, then how we can do that? So for particles which have zero or integral spin, we can characterize them by the symmetric wave function. That means that these particles do not need to obey the Pauli's exclusion principle. Thus, for a system of bosons, the wave function for the complete system is given by the symmetric wave function, which is given as mathematically psi subscript s particle 1, 2, so on till n is equal to 1 upon under root n factorial times delta whole times summation over p permutation operator p acting on the state phi 1 subscript alpha 1 1, phi 2 subscript alpha 2 2, and so on to phi alpha subscript alpha n n, where the term delta represents a factor which depends on the number of particles occupying the same state. So here, why is this delta important? Because since these particles are indistinguishable, it is impossible to associate a specific particle with a particular state. All that we can say is that these many number of particles are occupying this particular state, but we cannot individually identify as to which particle is occupying which state. And this is precisely the situation that leads to the Bose-Einstein statistics. That is, it leads to the statistics which governs the particles which have zero or integral spin. So students, now let us summarize what we have learned in this module. Firstly, we got to know what do we mean by identical particles and what conditions are required for us to know whether the particles are identical or not. Having known that, we then learnt the principle of indistinguishability of identical particles, and thereby we realized the difference between classical mechanics and quantum mechanics in terms of dealing with such particles, because classical mechanics does not have any indistinguishability element or criteria. Then we learnt through an example how the problem of identical particles is treated differently in quantum mechanics from that in classical mechanics. Then, having learnt the properties of permutation operators, you will now be able to construct the completely symmetric and completely antisymmetric wave functions. And using these wave functions, you will be able to define one set of indistinguishable and identical particles, which are called fermions, which will be governed by the antisymmetric wave functions, and the other set of particles, which are called bosons, which will be governed by the symmetric wave function. Then we will also be able to find the connection between the spin and the statistics and learn the Pauli's exclusion principle. And finally, we will know the definition of the fermions and the bosons. Thank you.